Picture a desk in Princeton, sometime in the autumn of 1936. On that desk sits a manuscript written in careful English by a young mathematician who has only recently arrived from Cambridge. The pages are dense with symbols, but buried inside them is a proof that will change what humanity believes it can know. The mathematician's name is Alan Turing. He is 24 years old, and the thing he has just demonstrated is that there exist questions no procedure, no machine, no calculation running for any finite stretch of time can ever answer. Not questions we haven't solved yet, not puzzles waiting for a cleverer mind. These are questions that mathematics itself has walled off from us, permanently, provably, with the finality of a locked door whose key does not exist. For almost a century now, that proof has stood. It belongs to a family of results that includes Kurt Gödel's incompleteness theorems from 1931, Alonzo Church's parallel finding about logical validity from 1936. Together they form a kind of border around what thinking can accomplish. On one side of the border is everything we can compute, everything we can decide, everything that yields to logic given enough time and enough steps. On the other side are the undecidable questions, statements that are either true or false, but which no finite procedure will ever determine, and yet. Buried inside the mathematics of Albert Einstein, inside the field equations of general relativity that describe how mass and energy curve spacetime itself, there exist solutions that seem to offer a loophole. These solutions describe universes, or regions within universes, where something very strange happens. Along certain paths through spacetime, an infinite amount of proper time elapses for one observer, while only a finite amount passes for another observer nearby. In such a geometry, a computation that would require an eternity to complete could, in principle, finish, and send its answer back to someone who has waited only an afternoon. Some physicists dismiss these spacetimes as mathematical curiosities, artifacts of equations taken too literally, but others take them seriously. Philosophers of physics have written rigorous papers analysing them. Cosmologists have proposed physical scenarios in which they might actually exist, and the question they raise is extraordinary. Might the universe itself contain regions where the undecidable can be decided, where the incomputable can be computed, where Turing's wall has a door? This is not science fiction. It is a genuine open question in theoretical physics and the philosophy of mathematics. The spacetimes in question have a name, Malament-Hogarth spacetimes, after two researchers who formalised their properties in the 1980s and 90s. And over the next 2 hours, we are going to walk through the mathematics, the geometry, and the heated debate that surrounds them. If you find these slow explorations useful for thinking or for sleep, consider tapping that subscribe button. It helps more than you know. Now, let us begin. To understand what these strange spacetimes might accomplish, you first need to feel the weight of the problem they claim to solve. And to feel that weight, we need to visit the moment when Alan Turing first drew the boundary around the computable. It is 1936, and Turing is responding to a challenge that stretches back almost a decade. In 1928, the German mathematician David Hilbert, the most famous mathematician alive, the grand old man of the field, stood with his collaborator Wilhelm Ackermann and posed what they called the Entscheidungsproblem, the decision problem. Hilbert wanted to know whether there existed a general mechanical procedure, an algorithm, that could take any mathematical statement expressed in first-order logic and determine in finite time whether that statement was true. Hilbert believed the answer was yes. He believed mathematics was fundamentally complete and decidable, that every true statement could in principle be proven, and that there was a method for finding those proofs. This was Hilbert's dream, a mathematics without mystery, a system where every question had a findable answer. Turing's paper destroyed that dream. He did not attack the problem head-on. Instead, he invented something new. A mental device that would come to be called a Turing machine. Imagine an infinitely long tape divided into squares, each square either blank or marked with a symbol. Imagine a reading head that moves along the tape, one square at a time, reading the symbol beneath it and then, based on its current internal state and the symbol it sees, writing a new symbol, moving left or right, and transitioning to a new state. The rules for what the machine does in each situation form its program. And Turing showed that this simple device, this tape and head, could in principle compute anything that any algorithm could compute. But here was the devastating part. Turing then asked, can we build a Turing machine that takes as input any other Turing machine and any input, and determines whether that machine running on that input will eventually halt, stop running, or will continue forever? The question sounds almost administrative. Will this program finish, or will it loop endlessly? Surely there must be some general method for answering it. Turing proved there is not. His argument is beautiful and strange. Suppose such a halting oracle exists. Call it H. You feed H a description of any machine M and any input I, and H tells you, yes, M will halt on I, or no, M will run forever. Now construct a new machine. Call it D for diagonalizer. That does the following. D takes as input a description of some machine M. D then asks the oracle H, will M halt if given its own description as input? If H says yes, D enters an infinite loop and runs forever. If H says no, D immediately halts. Now ask, what happens when you run D on its own description? If D halts when given its own description, then by D's definition, the oracle must have said it would not halt, but then D should have looped forever. Contradiction. If D runs forever, then the oracle said it would halt, but then D should have halted. Contradiction again. There is no escape. The oracle cannot exist. No Turing machine can solve the halting problem for all possible inputs. Stop and feel the weight of that. This is not a failure of effort or ingenuity. Turing did not prove that we haven't yet found the right algorithm. He proved that no such algorithm can exist, period, within the structure of computation itself. The undecidable is not waiting to be decided by a smarter mind. It is walled off by logic. The modern language we use, the halting problem, the clean formulation in terms of programs and inputs, is actually an elaboration developed after Turing. Scholars note that Turing's original paper did not use the phrase halting problem, and did not present the self-referential argument in quite the form we teach today. What Turing gave was a response to Hilbert-St-Scheidung's problem, showing that no mechanical method could decide the validity of arbitrary first-order statements. The halting problem is a later crystallization of the same idea, polished into its sharpest form. But the meaning is unchanged. There are functions that are perfectly well defined mathematically. You can write down exactly what they should output for every input, and yet no algorithm computes them. There are questions with definite answers that no finite procedure will ever reach. Turing's proof stood as a kind of melancholy triumph. It clarified the limits of mechanism. It gave birth to theoretical computer science. And it erected a permanent fence around what reasoning can accomplish. Alonzo Church, working at Princeton at the same time, arrived at the same conclusion by a different route. Using his lambda calculus, a formal system for expressing computation through function application, Church showed in 1936 that there is no general algorithm for deciding first-order logical validity. Church and Turing proved, independently and nearly simultaneously, that Hilbert's dream was impossible. And 5 years earlier, Kurt Gödel had already opened the crack. In 1931, Gödel published his paper über formell unentscheidbare Sätze der Principia Mathematica und verwandter Systeme, on formally undecidable propositions of Principia Mathematica and related systems. The title itself is a kind of death knell for a certain vision of mathematics. Gödel's first incompleteness theorem says this: any formal system that is powerful enough to express basic arithmetic, and that is consistent, meaning it doesn't prove contradictions, will necessarily contain true statements that cannot be proven within the system. The axioms you choose, no matter how cleverly selected, will always leave gaps. Some truths will escape. The sentence Gödel used to prove this is itself a marvel of self-reference. It says, in effect, this statement is not provable. If the statement were provable, it would be false, because it claims to be unprovable. But a consistent system should not prove false statements, so the statement must be unprovable. And since it accurately describes its own unprovability, it is true. A true statement the system cannot prove. Let me try once more to give you a feel for what this means. Imagine mathematics as a great building. with axioms as the foundation and theorems as the floors stacked above. Gödel showed that no matter how tall you build the structure, there will always be rooms you cannot reach from inside it. True propositions float above the highest floor, visible but inaccessible. Together, Gödel, Church, and Turing drew a map of the unmappable. They showed that undecidability is not a bug in our formal systems, it is a feature of mathematics itself. There will always be questions that cannot be answered by any finite procedure. This is the wall. For nearly a century it has seemed absolute, but Einstein's equations, as it turns out, describe a very strange universe. Albert Einstein published his general theory of relativity in November of 1915. It was the culmination of nearly a decade of struggle. False starts, conceptual revolutions, moments of despair and breakthrough. The result was a set of field equations that described gravity not as a force between masses, but as the curvature of spacetime itself. Mass and energy tell spacetime how to bend. Spacetime tells matter how to move. The equations are elegant, fiendishly difficult to solve, and startlingly generative. They do not describe a single universe. They describe a family of possible universes. Any geometry that satisfies the equations is mathematically a valid solution. And physicists quickly discovered that this family includes members far stranger than anything Einstein had imagined. The first exact solution came in that same year, 1915, from an unlikely source. Karl Schwarzschild was a German astronomer and physicist who had volunteered for the army at the age of 41 and was serving on the Russian front when Einstein published his equations. From the trenches in the midst of war, Schwarzschild managed to solve the field equations for the simplest possible case: empty space around a perfectly spherical, non-rotating, uncharged mass. His solution described what we now call a black hole. At a certain radius, the Schwarzschild radius, spacetime curves so severely that nothing, not even light, can escape. Inside that radius lies a singularity, a point where the mathematics breaks down, where curvature becomes infinite, where the known laws of physics cease to apply. Schwarzschild sent his paper to Einstein. Einstein replied, "I had not expected that one could formulate the exact solution of the problem in such a simple way." But Einstein was also disturbed. The solution implied structures that seemed impossible, regions of space-time cut off from the rest of the universe, singularities where physics gave way to meaninglessness. Schwarzschild himself did not believe his solution described anything real. He thought it was a mathematical curiosity, a consequence of the equations that nature would never actually produce. He died the following year, possibly from an autoimmune disease, pemphigus, contracted while serving at the front. He never saw the revolution his work would help create. For decades, physicists treated black holes as theoretical abstractions. The consensus was that real stars would not collapse so catastrophically, that some unknown mechanism would prevent the formation of these extreme objects. It took until the 1960s, half a century after Schwarzschild's solution, for black holes to be accepted as genuine physical possibilities, and until the 21st century for gravitational wave observatories to detect them directly. But Schwarzschild's solution was only the beginning. The field equations, once you let them run, generate a zoo of strange geometries, and each one teaches us something about what spacetime is capable of. In 1963, the New Zealand mathematician Roy Kerr found a solution that had eluded physicists for almost 50 years: the exterior field of a rotating massive object. The Kerr solution generalizes Schwarzschild to spinning black holes, and it is far stranger. A Kerr black hole has not one horizon but two. The outer event horizon is the point of no return, the surface beyond which escape is impossible. But inside that lies a second horizon, called the Cauchy horizon, a boundary beyond which the future is no longer determined by the past. The very structure of causality phrase. Around a rotating black hole lies a region called the ergosphere, where space-time is dragged along by the rotation so violently that nothing can remain still relative to distant observers. Frame dragging, this effect is called, the spinning mass literally drags the fabric of space-time around with it, and at the centre of a Kerr black hole lies not a point singularity, as in Schwarzschild's solution, but a ring singularity. a circle of infinite curvature where the mathematics weeps. Even this was not the strangest thing the equations could produce. In 1949, Kurt Gödel himself, the same Gödel who proved incompleteness, found a solution to Einstein's field equations that described a rotating universe. In Gödel's universe, the entire cosmos spins, and that rotation produces something extraordinary: closed time-like curves, paths through space-time that loop back on themselves, world lines along which a traveller could, in principle, return to their own past. Time travel, in other words, embedded in Einstein's equations. Einstein found this deeply troubling. He admitted that Gödel's solution was mathematically valid, but doubted it described physical reality. Most physicists agreed. Gödel's rotating universe requires exotic conditions, matter with unusual properties, a cosmological constant tuned just so, that do not match our observations of the actual universe. But the solution existed, the equations permitted it, and once you accept that Einstein's field equations can produce time loops, you must ask, what else can they produce? The answer, we now know, includes spacetimes where the relationship between time and computation breaks down entirely. Spacetimes where an observer at one location experiences only a finite duration, while an observer elsewhere accumulates infinite proper time. Spacetimes where the undecidable might in principle be decided. These are the spacetimes that David Malament and Mark Hogarth would study, formalize, and give their names to. But before we meet them, we need to understand what makes a spacetime strange enough to accomplish this feat. Let that settle for a moment. The equations of general relativity do not describe our universe. Not directly, not uniquely. They describe a class of possible universes, a landscape of geometries. Some of those geometries are tame. They match our observations, our experience, our intuitions about cause and effect. Others are wild. They contain time loops, singularities, horizons where causality shreds. And the question that haunts theoretical physics is, which of these geometries are physical? Which ones could nature actually build? The Schwarzschild solution seemed wild in 1915. By the 1970s, astronomers were detecting X-ray binaries, systems where a star was being devoured by something invisible and compact, its matter spiraling inward and blazing with energy as it fell toward an event horizon. Black holes had crossed from speculation to observation. The wild had become real. The Kerr solution describes the black holes we actually see, the supermassive objects at the centers of galaxies, the stellar mass holes that merge and ring like bells in gravitational wave data. Most of them spin. The Kerr geometry, with all its horizons and ergospheres and ring singularities, is the geometry that nature has built. What then of the other solutions? What of Gödel's rotating universe, with its closed time-like curves? What of the even stranger geometries that Malament and Hogarth would explore? Spacetimes where infinite computation might be possible, where the halting problem might have a physical answer. Physics has a name for this kind of question. It's called the question of cosmic censorship. Roger Penrose's conjecture that nature conspires to hide singularities behind horizons, preventing them from influencing the wider universe. It's the question of chronology protection. Stephen Hawking's conjecture that the laws of physics somehow prevent the creation of time machines. It's the question, at bottom, of whether the equations are smarter than nature, or whether nature is smarter than the equations. We do not know the answer. We have conjectures, arguments, partial results. We have physicists who believe the exotic solutions are mathematical artifacts, and physicists who believe they might point to something real. The debate is not settled. The equations leave the door ajar, and that ajar door is where our story is headed. But first, we need to feel the architecture of the problem. We need to understand what it would mean for a spacetime to allow infinite computation in finite time. Imagine you have a problem that would take forever to solve, not a long time, but literally forever. An infinite number of steps. Perhaps you're searching for a counterexample to some conjecture, checking every integer in turn, and you don't know if you'll ever find one. On any ordinary computer, running in ordinary time, this task cannot be completed. You would need to wait an eternity, and eternity does not arrive. But now imagine a different geometry. Imagine two observers, Alice and Bob. Alice sets off on a journey through space-time carrying a computer. She programs it to run the infinite search. If it ever finds the answer, it will send a signal. Bob stays behind. In ordinary spacetime, this doesn't help. If Alice needs infinite proper time to complete her calculation, she will age forever before she finds the answer. Bob will wait forever too. Nothing is gained. But Malament-Hogarth spacetimes are not ordinary. In these geometries there exist world lines, paths through spacetime, along which Alice can experience infinite proper time, while Bob, waiting at a particular point, experiences only finite time. Alice runs her infinite computation, and if it halts, she sends a signal. Bob waits his finite wait. If the signal arrives, he knows the answer is yes. If it doesn't, he knows the answer is no. The halting problem in such a spacetime becomes decidable. This sounds like magic. It sounds like cheating, and perhaps it is. The question is whether such spacetimes can actually exist, whether the universe permits their construction, or whether some law of physics, some cosmic censor, forbids them. That is the question we are going to pursue. We will meet Malament and Hogarth. We will trace the mathematical structures they identified. We will enter the interior of rotating black holes and confront the Cauchy horizon, the place where the future becomes indeterminate. We will ask whether these spacetimes can carry information reliably, whether signals can survive the journey across infinite proper time, whether the whole scheme collapses under its own weight. And we will find that the physicists are divided. Some dismiss Malament-Hogarth spacetimes as irrelevant, unphysical, impossible. Others take them seriously, not as practical devices, but as probes of the relationship between physics and computation, windows into what the universe might permit. The stakes could not be higher. If such spacetimes are possible, then the limits Turing discovered are not absolute. They are local, features of our particular geometry, our particular slice of the cosmos. Somewhere else, in principle, the undecidable might yield, that somewhere else is where we're going. But to get there, we first need to understand the architecture of the infinite errand, the precise geometry that would allow a computation to run forever and still deliver its answer in time. Rest with that for a moment. The mathematics of undecidability seemed final. The wall seemed permanent. But the equations of general relativity describe a vast landscape of possible geometries, and in some corners of that landscape the wall might have a door. Whether that door opens onto anything real, whether the universe contains such geometries, whether signals can cross them, whether the answer could ever reach us, that is the question we will spend the next 2 hours exploring. Let us continue. The 1980s and 1990s saw a small but dedicated group of researchers turn their attention to these questions. They came from philosophy of physics, from mathematical logic, from the study of spacetime structure. They asked, what would it take for a spacetime to allow an infinite computation to be completed in finite observer time? What conditions must the geometry satisfy? And are there solutions to Einstein's equations that meet those conditions? The answers they found were surprising. The geometries exist. They are mathematically valid, fully consistent solutions to the field equations. The question of whether they are physically realizable, whether nature would build them, whether any real observer could exploit them, that remains contested. But the mathematics is clear. David Malament, a philosopher of physics at the University of Chicago, began exploring these structures in the 1980s. He asked a precise question. What does it mean for a spacetime to allow an observer to survey an infinite amount of proper time experienced by another observer, while experiencing only finite proper time themselves? The answer required careful definitions. In general relativity, proper time is the time measured by a clock travelling along a particular world line, a path through space-time. Different world lines can experience different amounts of proper time between two events, depending on the geometry they traverse. This is the origin of the famous twin paradox. Two observers who take different paths through space-time will age differently. Malament identified geometries where this difference could be infinite. One observer travels along a world line that accumulates infinite proper time. Another observer remains at a point, or traverses a path of their own, that accumulates only finite proper time, and crucially, the infinite world line remains within the past-like cone of the finite observer's final moment. Whatever happens along that infinite journey can, in principle, send a signal that arrives before the finite observer's wait is over. Mark Hogarth, a researcher working in the same tradition, formalized these ideas further in the 1990s. He gave them a precise mathematical definition and explored their implications for computability theory. If you could station a computer along the infinite world line, program it to solve an undecidable problem, and wait at the finite endpoint, you could, in principle, receive the answer. The spacetimes that allow this came to be called Malament-Hogarth spacetimes. They are not exotic add-ons to general relativity. They are honest solutions to Einstein's field equations. They exist within the mathematical framework that describes our universe. But do they describe our universe? That is the question that John Earman and John Norton, two philosophers of physics, would take up in a series of papers that brought these ideas to broader attention. They examined the conditions under which Malament-Hogarth spacetimes could exist, the physical problems they faced, and the implications they carried for our understanding of computation and physics. We will follow their arguments. We will enter the interior of Kerr black holes and ask whether they provide the geometry Malament and Hogarth require. We will confront the Cauchy horizon, the surface where determinism breaks down, and the instabilities that threaten to destroy any signal trying to cross it. The journey will be strange. The conclusions will be uncertain. But the questions are real, and serious people are asking them. Let me try once more to give you a feel for the stakes. Alan Turing proved, in 1936, that certain questions cannot be answered by any finite procedure. His proof seemed absolute. It applied to any computer, any algorithm, any mind that operates by finite steps in finite time. But Turing's proof assumed something about time. It assumed time was ordinary, that an infinite computation required an infinite wait. What if time, in some regions of the universe, does not work that way? What if the geometry of space-time itself provides a shortcut, a fold, a path where infinity and finitude meet? The field equations of general relativity describe many geometries. Some are tame, some are wild, and among the wild ones are spacetimes where the relationship between computation and time breaks down in exactly the way that would let an infinite calculation finish in finite observer time. Whether these spacetimes are physical, whether nature permits them, whether observers could exploit them, whether the undecidable could become decidable, that is the question at the heart of this documentary. We do not know the answer. The physicists are divided. The philosophers are divided. The equations sit silent, offering possibilities without judgments. But the question is no longer whether such spacetimes are mathematically possible. Malament and Hogarth proved they are. The question is what, if anything, they mean for the universe we actually inhabit. The answer may be nothing. The answer may be everything. We're going to find out. The answer begins with a diagram, not a photograph, not a simulation, but a simple curve drawn on paper. David Malament, working through the late 1970s and into the 80s, was not yet asking about computation. He was asking a different question, one that sounds almost innocent until you follow it to its conclusion. He wanted to know what the causal structure of space-time, the pattern of which events can influence which other events, could tell us about the geometry of the universe. His foundational work, published in 1977, showed that if you know the causal relations between events in a space-time, you can recover almost everything about its geometry. The speed of light traces out the skeleton. The rest follows. But Malament was also a philosopher, and philosophers notice things that physicists sometimes take for granted. He noticed that the relationship between proper time and causal structure was stranger than it appeared. Two observers could start at the same event, take different paths through space-time, and arrive at the same final event having aged by different amounts. This was familiar. This was the twin paradox, taught in undergraduate courses, confirmed by experiment. The strangeness came when you pushed the geometry further, when you asked, how different could those ages be? Picture the diagram, a vertical axis representing time, a horizontal axis representing space, two world lines, each beginning at the same point at the bottom of the page. One curves gently upward and to the right, eventually bending back to meet a point near the top. The other spirals outward, looping and winding, stretching toward the edges of the page while always remaining in the pass-like cone of that same final point. The first world line is short. An observer travelling along it experiences a finite amount of proper time. The second world line is long. An observer travelling along it experiences more proper time, much more. And in certain geometries, Malament realised that second world line could be infinitely long in proper time, while still lying entirely within the causal past of the first observer's final moment. Let that settle for a moment. An infinite journey, contained within a finite wait. An eternity of experience for one observer, all of it visible, all of it potentially signalling, to another observer who has aged only a finite amount. The geometry of space-time itself creates a funnel, a channel, a corridor through which infinite proper time can pour into a finite causal interval. Malament did not immediately frame this in terms of computation. He was interested in the structure of time, the shape of causality, the geometry of possible worlds permitted by Einstein's equations. But the computational implications were waiting, implicit in the mathematics. If one observer could experience infinite proper time while remaining in another observer's past, then in principle, that observer could perform an infinite number of operations, an infinite computation, and send the result before the finite observer's clock runs out. This is not a trick of words. This is not a metaphor. It is a mathematical fact about certain solutions to the Einstein field equations. The geometry permits it. The question, as always, is whether nature does. Let me be careful here. Malament's insight was not that such spacetimes definitely exist in our universe. His insight was that they are valid solutions, that the equations of general relativity, the equations that describe gravity as the curvature of spacetime, admit these configurations as possibilities, just as the equations admit black holes and gravitational waves and the expansion of the universe. They also admit spacetimes where infinity and finitude interweave in this strange way. The framework that emerged around these ideas, developed through the 1980s and into the 1990s, gave them a name. Hogarth formalized the definition. A Malament-Hogarth spacetime is a spacetime manifold, a mathematical space equipped with the geometry of general relativity, that contains a world line with infinite proper length lying entirely within the chronological past of some event. The event is called the Malament-Hogarth event. The world line is called the infinite curve, and the observer who reaches the Malament-Hogarth event in finite proper time is the one who could, in principle, receive the results of an infinite computation. Now picture the setup in more human terms. We will call the observer on the infinite curve Alice. We will call the observer at the Malament-Hogarth event Bob. Alice sets off on a journey. Her journey, in her own experienced time, goes on forever. She ages without limit. Birthdays accumulate into centuries, centuries into millennia, millennia into eons beyond counting. Her clock never stops. Her world line stretches outward through proper time without bound. And yet, and here is the strange part, the part that violates every intuition about time and waiting and finitude. Every moment of Alice's infinite journey lies in Bob's past. Every signal Alice sends, every result she computes, every discovery she makes, all of it can reach Bob before his own clock reaches a particular reading. Bob waits for a finite amount of his own proper time, and during that finite wait, the entirety of Alice's infinite existence unfolds in his causal past. Think about what that means. Alice could be programmed with a task. She could be given a Turing machine, a computer, an algorithm designed to check something, to test every integer, to examine every case, to search through an infinite space for a counterexample. In ordinary space-time, this would be hopeless. The search would take forever. Bob would die waiting. His descendants would die waiting. The heat death of the universe would arrive before the computation finished. But in a Malament-Hogarth space-time, Alice's forever fits inside Bob's finite wait. If Alice ever finds what she's looking for, she sends a signal. The signal, travelling at or below the speed of light, arrives at Bob's location before his clock runs out. And if Alice never finds it, if the search goes on forever, through every integer, every case, every possibility, without ever finding a counterexample, then no signal arrives. The absence of a signal is itself information. It tells Bob that the search was exhaustive, that every case was checked, that no counterexample exists. This is the architecture of an infinite errand. Alice runs forever. Bob waits a finite time, and the answer arrives one way or another. Let me try once more to make this feel physical. Imagine a relay race, but the track is not a circle. It is a spiral stretching outward through space-time. The runner begins at the center and sprints outward, carrying a baton. The finish line is not at the end of the track, it is at a point in space-time where the race clock shows a finite reading. The geometry of the spiral is such that no matter how far the runner goes, no matter how many laps, how many miles, how many light years, the baton can always be passed to someone who reaches the finish line before the clock runs out. The runner can run forever. The baton always arrives in time. This is not ordinary space. This is not ordinary time. This is a geometry where the relationship between distance travelled and time elapsed is warped, curved, folded in ways that permit infinity to fit inside a finite interval. The 1993 paper by John Earman and John Norton, titled "Forever is a Day," made this architecture explicit. They examined the mathematical conditions under which Malament-Hogarth spacetimes could exist. They explored the physical problems such spacetimes faced, and they asked what it would mean for computability if such spacetimes were real. Their title captures the paradox perfectly. Forever is a day, an infinite duration compressed by geometry into a finite interval. The phrase sounds poetic, but the mathematics is precise. Earman and Norton identified several spacetimes that possess the Malament-Hogarth property. Some are familiar. The Kerr metric, which describes the spacetime around a rotating black hole, belongs to this class. An observer could, in principle, orbit the black hole indefinitely, experiencing infinite proper time, while another observer falls through the event horizon and reaches a point where all of that infinite orbit lies in their causal past. The rotating black hole, discovered by Roy Kerr in 1963, is not merely a theoretical curiosity. Astronomers believe most black holes in the universe rotate. The geometry that permits Malament-Hogarth configurations may be out there, surrounding collapsed stars and galactic cores, woven into the fabric of the cosmos. But there is a problem. There is always a problem. The inner horizon of a Kerr black hole, the boundary inside which the Malament-Hogarth geometry becomes possible, is believed to be unstable. Radiation falling into the black hole from outside gets blue shifted as it approaches the inner horizon. The energy piles up. The blue shift grows without bound. And according to most calculations, this concentrated energy creates a singularity, a breakdown of the geometry, right where the Malament-Hogarth event should occur. The infinite computation cannot cross the threshold. The signal is destroyed before it arrives. This is not a minor technical difficulty. It is a fundamental threat to the entire program. If the Kerr interior is unstable in the way most physicists believe, then rotating black holes cannot serve as venues for hypercomputation. The geometry permits it, the physics forbids it. Earman and Norton catalogued other examples. The Reissner-Nordström spacetime, which describes a charged but non-rotating black hole, also has Malament-Hogarth features. So does anti-de Sitter spacetime, a cosmological model with a negative cosmological constant. So does Gödel's rotating universe, the strange solution Kurt Gödel discovered in 1949 while walking with Einstein in Princeton. Each of these spacetimes permits the existence of infinite world lines in the causal past of finite events, but each also has problems. Anti-de Sitter spacetime violates the strong energy conditions, the assumptions about the behavior of matter and energy that physicists generally consider reasonable. Gödel's spacetime contains closed time-like curves, paths through spacetime that loop back on themselves, permitting a form of time travel that most physicists consider pathological. Reissner-Nordström spacetime, like Kerr, exhibits a divergent blue shift at the inner horizon, threatening to destroy any signal before it can be received. Every candidate venue has a flaw. Every geometry that permits the infinite errand also harbours an instability, a violation, a breakdown that threatens to close the loophole before it can be exploited. This is the pattern Earman and Norton documented. The equations of general relativity permit Malament-Hogarth spacetimes. They are mathematically valid. They satisfy the field equations. They describe possible configurations of matter and geometry. But the additional conditions that physicists impose, energy conditions, stability requirements, the absence of causal pathologies, tend to rule them out. One condition deserves special attention. It is called global hyperbolicity. A globally hyperbolic spacetime is one in which the initial conditions on a particular surface determine the entire future evolution of the system. Physics works the way we expect it to work. Give me the state of the universe at one moment, and I can predict what happens next. Global hyperbolicity is determinism made geometric. Malament-Hogarth spacetimes are never globally hyperbolic. They cannot be. The very feature that makes them interesting, the existence of infinite world lines in the causal past of finite events, breaks the deterministic structure that global hyperbolicity requires. If you could compute an undecidable result and send it to an observer in finite time, you would be adding information to the universe that was not contained in any initial conditions. The future would depend on something beyond the past. This is connected to Roger Penrose's cosmic censorship hypothesis, one of the most important conjectures in general relativity. Penrose proposed that physically reasonable spacetimes hide their singularities behind event horizons, preventing them from influencing the outside universe. Strong cosmic censorship goes further. It asserts that physically reasonable spacetimes are globally hyperbolic. If Penrose is right, then Malament-Hogarth spacetimes cannot describe the physical universe. They are mathematical curiosities, permitted by the equations but forbidden by nature. But cosmic censorship is a hypothesis, not a theorem. It has been proven in some special cases and violated in others. The question of whether the universe respects global hyperbolicity remains open. The equations are silent. The evidence is incomplete. Let me pause here and return to the human scale. What Malament and Hogarth discovered, what Ehrman and Norton formalized, is that the computational limits Turing proved in 1936 rest on an assumption about the structure of time. Turing assumed that infinite computations require infinite time for all observers. He assumed that finitude is absolute, that no shortcut exists, that the only way to check infinitely many cases is to wait forever. General relativity suggests otherwise. The equations permit geometries where finitude and infinity are relative, where one observer's eternity is another observer's afternoon. In these geometries, the undecidable might become decidable, not by finding a faster algorithm but by finding a stranger spacetime. The philosophical implications are profound. If Malament-Hogarth spacetimes are physical, then the limits of computation are not limits of logic alone, they are limits of physics. They depend on the geometry of the universe. What can be computed is not an abstract mathematical question. It is a question about the shape of space-time, the curvature of gravity, the structure of cosmic horizons. But if Malament-Hogarth spacetimes are unphysical, if every candidate is ruled out by instabilities, energy condition violations, or cosmic censorship, then Turing's limits stand. The undecidable remains undecidable, not because of logic, but because the universe does not provide the geometry required to escape. Either way, the relationship between computation and physics is deeper than it appears. The borders of the computable are drawn not in the abstract space of mathematics, but in the curved fabric of space-time itself. We have now met the key idea, an infinite world line in the causal past of a finite event. Two observers, one experiencing eternity, one waiting a finite interval, linked by a geometry that permits signals to travel from one to the other, a loophole in the logic of undecidability, opened by the equations of general relativity. The question that remains is whether the loophole is real. John Ehrman and John Norton approached this question with the rigor of philosophers trained in physics. They were not trying to prove that hypercomputation is possible. They were trying to understand the conditions under which it might be and the conditions under which it certainly is not. Their work was diagnostic, not promotional. They wanted to know what the universe permits and what it forbids. In the process, they mapped the landscape of Malament-Hogarth spacetimes more thoroughly than anyone before. They identified the families of solutions that possess the required property. They catalogued the problems each family faces. They analysed the blue shift instabilities, the energy condition violations, the causal pathologies that threaten to close every loophole, and they reached a conclusion that was neither triumphant nor dismissive. The conclusion was, maybe, the equations permit it. The physics is uncertain, the question is open. This is the state of the field as we find it today. Malament-Hogarth spacetimes are mathematically valid. They are not ruled out by general relativity itself, but they face serious physical objections, and no one has yet demonstrated that they describe any region of the actual universe. We will explore those objections in detail. We will enter the Kerr interior and ask what happens at the inner horizon. We will confront the Cauchy surface and the breakdown of determinism. We will ask whether any signal, no matter how carefully sent, could survive the journey from an infinite world line to a finite observer. The geometry permits the impossible. Whether the universe does, that remains to be seen. For now, rest with this. The border between the computable and the uncomputable may not be a wall, it may be a horizon, and horizons, in general relativity, are not always what they seem. They depend on where you stand. They depend on how you move. They depend on the curvature of the spacetime through which you travel. Alan Turing drew a border in 1936. David Malament drew a diagram in the 1980s, and the question that connects them, the question of whether infinity can fit inside a finite weight, is still, to this day, unanswered. The equations leave the door ajar. We are going to walk through it. Mark Hogarth was not content with a diagram. What Malament had sketched was a possibility, a geometric intuition, a suggestion that the fabric of spacetime might harbour paths where infinity nests inside a finite interval. But possibility is not proof. Intuition is not protocol, and suggestion is not a mechanism you can examine, critique, and test against the standards of mathematical logic. Hogarth wanted the mechanism. He was a philosopher at Cambridge, trained in the foundations of physics and the philosophy of computation, and he understood that the question Malament had opened could not be answered by pictures alone. If Malament-Hogarth spacetimes were to matter, if they were to say something deep about the nature of computation and its relationship to physical law, then someone had to show exactly how a computation might exploit the geometry. Someone had to write down the protocol. Someone had to specify the machines, the signals, the clocks, the weighting, and the decision procedure that would follow. Someone had to prove that the protocol works, assuming the geometry is as described. In 1992, Hogarth published a paper in Foundations of Physics Letters. The title was a question: does general relativity allow an observer to view an eternity in a finite time? The answer, Hogarth argued, was yes, under certain geometric conditions. But more importantly, the paper laid out what viewing an eternity would mean in practice. 2 years later, he followed with a second paper, this one in the proceedings of a philosophy of science conference, Non-Turing Computers and Non-Turing Computability. Together with his doctoral thesis at Cambridge, completed in 1996, these works gave Malament-Hogarth spacetimes their rigorous definition and their computational interpretation. Let us follow the protocol exactly. Precision matters here. The loophole only works if every step is unambiguous. Imagine two observers. We have met versions of them before, but now they must be specified with care. Call them Alice and Bob. Alice will perform the computation. Bob will receive the result. They begin together at some event in spacetime, and then they part ways. Alice travels along the infinite world line, the path of unbounded proper length that is entirely contained in the chronological past of a certain event. Bob travels along a different path, one of finite proper length that terminates at that same event. The event where Bob arrives is the Malament-Hogarth event. It is the location where the answer will be known. Alice carries a machine. The machine is a Turing machine, or something equivalent, a device capable of performing any computation that a Turing machine can perform. Alice is given a candidate program and a candidate input. The question she's tasked to answer is, does this program, running on this input, ever halt? Does it ever reach a final state and stop? Or does it run forever, cycling through computation after computation, never terminating? This is the halting problem. Turing proved in 1936 that no algorithm can solve it in general. For any proposed decision procedure, there exists some program and some input for which the procedure gives the wrong answer or fails to halt itself. The undecidable is walled off from finite computation. No machine, given finite time, can answer every instance of the question. But Alice does not have finite time. Alice has infinite proper time. Her world line stretches on without bound. She can run the candidate program for as long as it takes. If the program halts after 1 trillion steps, she can wait 1 trillion steps and observe the halt. If it halts after a Google steps, she can wait a Google steps. If it halts after any finite number of steps, no matter how large, she will eventually see it halt. And here is the crucial instruction. If and when Alice's machine halts, she sends a signal to Bob. The signal travels through space-time. It follows a causal path, a trajectory that respects the geometry, moving no faster than light, obeying the rules of general relativity. And because Alice's entire infinite world line lies in the chronological past of the Malament-Hogarth event where Bob arrives, every signal Alice might send, no matter how late along her journey, has time to reach Bob before his clock reads T. The geometry guarantees it. That is what it means for the event to be a Malament-Hogarth event. So Bob waits. His journey to the Malament-Hogarth event takes finite proper time. His clock ticks forward, second after second, approaching T. And as he arrives, he asks a simple question. Did he receive a signal from Alice? If yes, the program halted. Somewhere along Alice's infinite computation, the machine entered a stable state, stopped running, and Alice sent word. The signal arrived before Bob's clock reached T. The answer is halt. If no, the program did not halt. Alice ran the computation forever, truly forever, through infinite proper time, and the machine never stopped. No signal was ever sent. Bob arrives at T with his receiver silent. The answer is, does not halt. This is the protocol. It is airtight within its mathematical assumptions. If the geometry is as described, if the spacetime genuinely contains an infinite world line entirely in the causal past of a finite event, then the protocol decides the halting problem. It does not merely approximate an answer. It does not give a probabilistic guess. It yields the exact, certain, correct answer to a question that no finite Turing machine can answer. Hogarth's contribution was to show that this protocol works in any Malament-Hogarth spacetime, regardless of which solution to Einstein's equations generates it. The argument does not depend on the specific curvature or the specific distribution of matter and energy. It depends only on the geometric property that defines the class, an infinite world line in the chronological past of a finite event. Wherever that property holds, the protocol holds, and the protocol solves the halting problem. Let that settle. It solves the halting problem. It crosses a border that Turing proved uncrossable. It does so not by violating logic, but by exploiting geometry. The computation itself is ordinary, just a machine running a program, step after step, according to deterministic rules. The magic, if that is the right word, is in the spacetime. The geometry provides the time Alice needs and the connection Bob needs to receive the result. Within the mathematical world of general relativity, Hogarth had shown that undecidability is not absolute. It is conditional. It depends on the structure of the spacetime in which the computation takes place. In a spacetime without the Malament-Hogarth property, a spacetime where every infinite path is causally isolated from finite observers, Turing's limits hold. In a spacetime with the property, they do not. The question is no longer whether the mathematics permits it. The mathematics does. The question is whether the universe provides it, and that question belongs to physics, not logic. John Earman was not the sort of philosopher who accepted claims without examination. He had spent his career at the intersection of physics and philosophy, asking hard questions about the foundations of spacetime theory, about determinism and indeterminism, about the relationship between mathematical models and physical reality. He was affiliated with the University of Pittsburgh, a department with a long tradition of rigorous work in philosophy of science. And he had a collaborator who shared his temperament. John Norton, also at Pittsburgh, also committed to the project of understanding what physics actually says, not what we might wish it to say. When Earman and Norton turned their attention to Malament-Hogarth spacetimes, they did so not as advocates, but as investigators. Their 1993 paper, published in the journal Philosophy of Science, was titled Forever is a Day, Supertasks in Potowski and Malament-Hogarth Spacetimes. The title itself captured their approach. A supertask is a task requiring infinitely many steps completed in finite time. The paper asked whether such tasks could be performed in certain spacetimes, and whether the performance would be physically meaningful. They accepted the mathematics. That was not in dispute. Hogarth's protocol was valid. If a spacetime has the Malament-Hogarth property, then the protocol decides the halting problem. The logic was sound. The geometry was correctly described. The conclusion followed. But acceptance of the mathematics was only the beginning. Earman and Norton wanted to know what happens when you try to build the machine. What happens when you try to send the signal? What happens when you account for the physical processes, the measuring devices, the transmission media, the propagation of light, that any real computation would require? They put the idea on trial. The charges were not frivolous. Earman and Norton had identified genuine problems, physical obstacles that any advocate of hypercomputation would have to overcome. They approached the question with the care of attorneys who respect their adversary, but intend to expose every weakness in the case. The first charge concerned the reliability of the computation itself. Alice's machine must run for infinite proper time without error. Not a single bit can flip, not a single circuit can fail, not a single quantum fluctuation can disrupt the calculation. Any error at any point along the infinite journey could change the outcome. And over infinite time, even vanishingly unlikely errors become certain. The expected number of failures diverges. The machine degrades. The computation cannot be trusted. This is not a theoretical quibble. It is a fundamental problem in any physical implementation of infinite computation. No real device is perfectly reliable. All devices are subject to noise, wear, thermodynamic fluctuation, and eventual decay. A device that runs forever must somehow evade all of these, or the protocol fails. The second charge concerned the signal itself. Suppose Alice's machine halts. Suppose she sends a signal to Bob. The signal must travel through curved space-time, across potentially vast distances, through regions of potentially extreme conditions. What happens to the signal along the way? In many candidate Malament-Hogarth spacetimes, the signal faces a problem called blue shift. As the signal approaches certain horizons, particularly the inner horizons of black holes, its frequency increases, energy accumulates, the signal intensifies. In the limit, the blue shift diverges. A photon sent by Alice arrives at Bob with infinite energy. It is not a gentle message, it is a catastrophe. This is not a minor technical detail. Blue shift instability is a known feature of many spacetimes with inner horizons. General relativity itself predicts it. And a signal with infinite energy is not a signal at all. It is a singularity. It destroys the receiver rather than informing it. The third charge concerned the causal structure itself. Malament-Hogarth spacetimes, by definition, contain infinite world lines in the causal past of finite events. But this structure has consequences. In many cases, it implies the existence of a Cauchy horizon, a surface beyond which the future is no longer uniquely determined by the past. Determinism breaks down. The equations of motion no longer yield unique solutions. The spacetime becomes, in a precise sense, unpredictable. And if the spacetime is unpredictable, what can we say about the result of a computation performed within it? How can Bob trust that the signal he receives, or fails to receive, reflects the true outcome of Alice's calculation? The geometry that permits hypercomputation may also undermine the very notion of a reliable answer. Ehrman and Norton did not conclude that hypercomputation is impossible. That would have been too strong. The mathematics was valid. The objections were physical, not logical, and physical objections can sometimes be overcome by finding the right spacetime, the right configuration, the right shielding against instabilities and errors. Their conclusion was measured, diagnostic, honest. The equations permit it. The physics is uncertain. The question is open. This framing, the mathematics versus the physics, the validity versus the viability, became the central tension of the entire field. Subsequent researchers would return to Ehrman and Norton's paper again and again, treating it as the benchmark against which all claims about hypercomputation must be tested. The paper did not close the door. It opened a courtroom, and the trial continues. Now we must enter the most famous candidate venue, the place where the geometry is not an abstraction, but a description of objects scattered throughout the observable universe, the place where the Malament-Hogarth property might actually hold. We are going inside a rotating black hole. Roy Kerr was a mathematician from New Zealand, born in 1934, trained in the methods of differential geometry and tensor calculus that Einstein's theory demands. In 1963, he achieved something that had eluded physicists for nearly half a century. He found an exact solution to Einstein's field equations, describing a black hole that rotates. This was not a minor refinement. The Schwarzschild solution, discovered in 1915, described a black hole that does not rotate, a static, spherically symmetric object with a single event horizon surrounding a point singularity. But real celestial objects rotate, stars spin, galaxies swirl. Matter, as it collapses, conserves angular momentum. A black hole formed from a rotating star will itself rotate, and a rotating black hole is not the same as a static one. Kerr's solution changed everything. Subrahmanyan Chandrasekhar, the Nobel laureate who spent much of his career studying the mathematical physics of black holes, later described encountering Kerr's solution as the most shattering experience of his scientific life. What shattered him was the realization that this abstract mathematical object, this particular arrangement of numbers and tensors satisfying Einstein's equations, provides the absolutely exact representation of untold numbers of massive black holes that populate the universe. The Kerr black hole is not a curiosity, it is the standard model. When astronomers observe gravitational waves from merging black holes, they are observing Kerr black holes. When they image the shadow of a black hole at the centre of a distant galaxy, they are imaging something well described by the Kerr metric. The solution is more general than Schwarzschild's and more realistic. It is what the universe actually contains. And the Kerr interior is strange. Picture the exterior first. Far from the black hole, spacetime is nearly flat. Stars shine, light travels in straight lines, clocks tick at their accustomed rate. As you approach the black hole, spacetime curves, the gravitational field strengthens, and at a certain distance, a surface called the outer event horizon, something decisive happens. Light itself cannot escape. Any signal sent outward is bent back inward. The event horizon is not a physical surface. There is no wall, no barrier you could touch. It is a causal boundary. Cross it, and you can never return. In a Schwarzschild black hole, that would be the end of the story. You would fall inward, and within a finite proper time, you would reach the singularity, a point of infinite curvature, infinite density, where the known laws of physics break down. Your journey would end. But in a Kerr black hole, the singularity is not a point, it is a ring. The rotation of the black hole spreads the singularity into a circle, oriented in the plane perpendicular to the axis of rotation. This ring singularity is time-like, not space-like. In technical terms, this means it is not an inevitable destination. You are not forced to hit it. With the right trajectory, you can avoid the ring entirely. You can pass through it, emerging, according to the mathematics, into another region of spacetime on the other side. This is already strange. But there is more. Between the outer event horizon and the ring, singularity lies another surface, the inner horizon, also called the Cauchy horizon. This is the boundary that Ehrman and Norton worried about. This is where determinism fails. Outside the Cauchy horizon, the universe is predictable in the sense that general relativity allows. Given the state of affairs on one surface, the equations determine what will happen elsewhere. The past fixes the future. Cause leads to effect in an orderly procession. But inside the Cauchy horizon, that predictability breaks down. The equations no longer yield unique solutions. Multiple futures become mathematically compatible with the same past. The spacetime is no longer globally hyperbolic, a technical term meaning that the entire history can be reconstructed from initial data on a single surface. Within the Cauchy horizon, reconstruction fails. The future is not determined by the past. And here is the connection to Malament-Hogarth spacetimes. The Kerr interior, with its ring singularity and its Cauchy horizon, contains world lines of infinite proper length that lie entirely in the chronological past of finite events. The geometry permits it. An observer could travel along such a path, experiencing infinite proper time, while another observer waits a finite interval at a location reachable by signals from every point on that path. The Kerr black hole is a candidate venue for hypercomputation. This is not a marginal case. This is the most astrophysically realistic candidate in the entire catalogue of Malament-Hogarth spacetimes. Rotating black holes exist. They are not rare. There are millions of them in our galaxy alone. If hypercomputation is possible anywhere in the actual universe, the Kerr interior is the most plausible place to look, but plausibility is not proof, and the Kerr interior, for all its mathematical elegance, faces the objections that Ehrman and Norton raised. The Cauchy horizon is there, marking the edge of determinism. The blue shift is there, threatening any signal that approaches the inner surface. The stability of the entire interior structure is in question, as we will see when we examine what happens when even a tiny perturbation enters the picture. For now, rest with the strangeness of the venue itself, a ring of infinite curvature you can fly through. a horizon beyond which the future is not fixed, world lines that stretch to infinity, nested inside the gravitational geometry of a spinning collapsed star. The mathematics describes it. The equations balance. The solution is exact. Roy Kerr found it in 1963, working with pencil and paper, seeking a pattern that satisfied Einstein's demands. He found more than he could have anticipated. He found a window into a region where the rules we take for granted, the rules of cause and effect, of computation and its limits, of what can be known and what must remain unknowable, bend and twist and perhaps break. The Kerr black hole is not merely an astronomical object. It is a laboratory for the foundations of physics and the philosophy of computation. It is the place where Turing's border meets Einstein's geometry. And the question of what happens when they meet, whether the border holds or whether the geometry provides an escape, is the question that now confronts us. We have the protocol, we have the courtroom, we have the venue. What we do not yet have is stability. The Cauchy horizon that makes the Kerr interior a Malament-Hogarth candidate is also its most vulnerable feature, and the universe, it turns out, may not permit such fragile structures to survive. The geometry opens the door. But what waits on the other side of that door is not yet clear. The door stands open, the mathematics has drawn it ajar, the geometry permits passage, and the protocol waits for someone to walk through. But the universe is not a patient host, and the threshold of the Cauchy horizon is not a quiet place. Picture what happens to light as it falls into a black hole. From the outside, watching a beam of light descend toward the event horizon, you would see its frequency drop, its wavelength stretch, its colour shifting toward the red end of the spectrum and then beyond, into infrared, into radio, into wavelengths too long to see. This is the gravitational redshift, and it is familiar to anyone who has studied relativity even casually. Light climbing out of a gravity well loses energy. Light falling in gains it. But inside the black hole, inside the Kerr geometry specifically, something stranger occurs. There is a second horizon to cross, and at that second horizon the rules invert in a way that turns a gentle accumulation into a catastrophe. Roger Penrose noticed the mechanism first. The geometry of Kerr spacetime creates an asymmetry between what happens to an observer outside the black hole and what happens to an observer falling through. An observer hovering far from the black hole watching the universe go by reaches time-like infinity and infinite proper time. Their clock ticks forever. The cosmos unfolds in front of them without end. But an observer who crosses the event horizon and then falls toward the Cauchy horizon does so in finite proper time. Their clock ticks a finite number of times before they reach that inner surface. And here is where the catastrophe begins. Imagine a signal, a wave of a light, a pulse of radiation, anything electromagnetic, being sent periodically from outside, once per second, say, one pulse every second, forever, stretching into the infinite future of the external universe. Those pulses fall into the black hole, they cross the event horizon, they continue inward, and as the infalling observer approaches the Cauchy horizon, all of those pulses, the infinite stream of them, one per second for eternity, arrive in a finite interval. The spacing between them shrinks, the frequency rises. What was once per second becomes 10 per second, then 1,000, then 1,000,000, then more than any number you care to name. The pulses compress. Their frequency climbs toward infinity. Their energy, proportional to their frequency, climbs with them. This is the blue shift effect, and at the Cauchy horizon, it becomes unbounded. Every photon that ever fell into the black hole, every stray bit of radiation from the cosmic microwave background, every quantum fluctuation in the electromagnetic field, all of it piles up at the inner horizon in a wall of rising frequency and escalating energy. The observer falling toward the Cauchy horizon does not encounter a quiet threshold. They encounter the accumulated light of eternity, compressed into a final instant. Let that settle for a moment. Eric Poisson and Werner Israel formalized the consequences in 1989. They discovered a phenomenon they called mass inflation, and the name captures something of its violence. As radiation falls toward the Cauchy horizon, its energy density rises without bound. And in general relativity, energy density is equivalent to mass. It curves space-time, it gravitates. The infinite blue shift of the infalling radiation creates an infinite growth in the effective gravitational mass inside the black hole. The Cauchy horizon, which in the idealized Kerr solution is a smooth surface you could pass through, becomes in any realistic scenario a singularity, a place where the curvature of space-time diverges, where the tidal forces become infinite, where the equations themselves break down. The Kerr solution is exact, but exactness requires perfection. It requires that the black hole formed in complete isolation, with no radiation ever falling in, with no perturbation from the outside universe, with nothing to disturb the precise mathematical balance of the geometry. That kind of perfection does not exist in nature. Every real black hole is bathed in the cosmic microwave background. Every real black hole accretes matter, however slowly. Every real black hole receives, from the moment of its formation, a steady drizzle of radiation from the universe around it. And that radiation, no matter how faint, triggers the blue shift instability. The Cauchy horizon inflates. The effective mass inside diverges. The smooth inner surface of the Kerr solution transforms into something far more violent. Amos Ory extended the analysis in 1991, and what he found contains a strange duality. The singularity that forms at the Cauchy horizon is real. The tidal forces become infinite, the curvature diverges, the mathematics signals a breakdown. But Ory showed that the singularity is what physicists call deformationally weak. An object falling through would experience infinite tidal forces, yes, but the total tidal distortion, the cumulative stretching and squeezing integrated over the passage, would remain finite. You would be torn by infinite forces, but the tearing would not have infinite duration. You would pass through, damaged but perhaps not destroyed, into whatever lies beyond. This is a peculiar kind of hope. It does not say that the Cauchy horizon is safe. It says that the violence there is brief. The singularity is a spike, not a wall. An observer might survive it in principle, if survival is measured by whether the observer's world line continues on the other side, whether that observer remains functional, whether any apparatus they carry remains operational, whether any computation they are running remains uncorrupted, is a different question. And for the Malament-Hogarth protocol, that different question is the only one that matters. Consider Alice, falling along her infinite world line computing forever. Consider Bob, approaching the Cauchy horizon to receive her signal. The geometry permits the protocol. The world line exists. The causal structure allows Alice's signal to reach Bob before he crosses the inner horizon. But between Alice and Bob lies that wall of blue-shifted radiation, that spike of infinite tidal forces, that singularity born from the instability of the inner horizon. Even if Bob survives the crossing in the technical sense, even if his world line continues to the other side, the signal he is waiting for must also survive. The photons carrying Alice's answer must also pass through the blue shift catastrophe. And those photons, by the very nature of the blue shift effect, arrive at the Cauchy horizon with infinite frequency and infinite energy density. The signal is destroyed. The answer is lost. The protocol fails. This is the darkest moment in the story of Malament-Hogarth spacetimes. The mathematics opens a door and the physics slams it shut. The geometry permits hypercomputation and the instability forbids it. Turing's border, which seemed for a moment to have a gap in the fence, proves to be guarded after all. Not by logic, but by the universe's refusal to permit perfect structures to endure. The work of a generation of physicists converges on this point. Penrose identified the blue shift mechanism. Poisson and Israel quantified the mass inflation. Ory clarified the nature of the resulting singularity, and in 2023, a mathematical proof formalized what numerical simulations had long suggested. The Cauchy horizon inside a perturbed Kerr black hole develops an instability that transforms it into a curvature singularity. The proof applies to the linearized vacuum Einstein equations. A simplification, yes, but a rigorous one. The instability is not an artifact of numerical error. It is not a peculiarity of special initial conditions. It is built into the geometry. It is waiting for any radiation that falls in. It is, in a precise mathematical sense, inevitable. And for anyone hoping to solve the halting problem by falling into a black hole, inevitability is the end of the road, or so it seems. The story does not end at the Cauchy horizon, because physicists are stubborn, and because the protocol that Hogarth devised contains more flexibility than a single scenario might suggest. The Kerr interior is the most astrophysically realistic candidate for hypercomputation, but it is not the only one. And even within the Kerr geometry, the blue shift instability is not the only obstacle. There are other problems, other objections, other ways the universe might forbid what the equations seem to allow. To understand whether any path remains open, we need to examine the full catalogue of difficulties and the attempts, some ingenious, some desperate, to engineer around them. Consider the signal itself. Alice, in the Hogarth protocol, is computing forever. She's running a Turing machine, checking whether a given program halts. If the program halts, she sends a signal. If it does not, she sends nothing. The protocol depends on Bob being able to distinguish between signal received and signal not received. But Bob is waiting at the Cauchy horizon, where every signal that ever entered the black hole arrives in compressed form. The blue shift does not affect only Alice's signal. It affects everything. The cosmic microwave background is blue shifted. Stray photons from distant stars are blue shifted. Quantum fluctuations in the vacuum are blue shifted. Bob is not listening in silence for a single clear tone. He's listening in a cacophony of infinite noise for a signal that may or may not have been sent. Ehrman and Norton raised this objection in their 1993 paper. They called it the divergent blue shift problem, and they were blunt about its implications. Even the slightest thermal noise, they wrote, will be amplified to such an extent that communication is all but impossible. The signal-to-noise ratio does not merely degrade, it collapses. Alice's signal, if it exists, is drowned in a sea of amplified static. Bob cannot distinguish the answer from the noise. The computation may have succeeded, but the result is unrecoverable. This is not a theoretical quibble. This is a fundamental limitation on any protocol that relies on sending information toward a Cauchy horizon. The blue shift does not care about the content of the signal. It amplifies everything equally. An infinite amplification of finite noise is infinite noise. No encoding scheme can overcome it. No error correction protocol can filter it out. The mathematics is unforgiving. There is another objection, subtler but equally damaging. In some Malament-Hogarth spacetimes, not the Kerr geometry specifically, but others in the catalogue, the world line that Alice must travel requires infinite acceleration. She is not merely falling. She is not merely coasting along a geodesic. She is actively propelling herself along a trajectory that demands more and more thrust as time goes on. The total acceleration, integrated over her infinite journey, diverges. The fuel required is infinite. The rocket is impossible. Ehrman and Norton examined this problem in the context of anti-de Sitter spacetime, one of the mathematical examples where Malament-Hogarth events exist. In that geometry, the observer playing Alice's role must accelerate without bound. The energy requirements are not merely large, they are infinite. No physical rocket, no matter how efficient, can supply what the trajectory demands. The protocol is unimplementable even in principle. The Kerr geometry avoids this particular problem. Alice can fall freely along a geodesic, experiencing no acceleration at all, while still traversing a world line of infinite proper time. The Kerr interior is more forgiving in this regard, but the blue shift problem remains, the signal degradation remains, the Cauchy horizon instability remains, and so the question becomes, is there any way to engineer around these obstacles? Is there any design, any configuration, any clever trick that might allow the protocol to succeed despite the hostility of the environment? In 2002, Gabaratisi of the Yukawa Institute and Istvan Nemeti of the Renyi Institute published a paper that attempted exactly this. They were not naive about the difficulties. They knew the objections. They had read Ehrman and Norton. They understood the blue shift, the noise, the instability. But they believed that careful engineering might make a difference. They believed that the protocol, properly designed, might survive what seemed like fatal obstacles. Atisi and Nemeti focused on the Kerr geometry specifically. They chose it because it was astrophysically realistic, because it avoided the infinite acceleration problem, because it was the best candidate in the catalogue, and they asked, what if we design the computer carefully? What if we choose the encoding scheme wisely? What if we position the observers precisely? Can we squeeze through the gap before the blue shift destroys everything? Their analysis was detailed. They examined the causal structure of Kerr spacetime, tracing the paths that signals could follow, calculating the time available before the Cauchy horizon instability set in. They showed that certain logical relations on natural numbers, certain specific computational questions, could in principle be decided in Kerr spacetimes. The mathematics permitted it, the geometry allowed it, the world lines existed. But their conclusion came with a caveat, and the caveat was severe. The obstacles they identified, the infinite acceleration in some spacetimes, the divergent blue shift in others, could be avoided only if chronology was violated. Only if the spacetime contained closed time-like curves, only if time travel was permitted. Let that phrase settle. Closed time-like curves are world lines that loop back on themselves. An observer following such a curve returns to their own past. They meet their earlier self. They violate causality in the most direct way imaginable. The Gödel universe contains such curves. The Kerr geometry, in its maximally extended form, may contain them, but closed time-like curves are precisely the structures that most physicists believe cannot exist in the real universe. They lead to paradoxes. They undermine the logical foundations of physics. They are the reason that Stephen Hawking proposed his chronology protection conjecture, the hypothesis that the laws of physics conspire to prevent time travel, that any attempt to create closed time-like curves will be thwarted by some mechanism we may not yet fully understand. Etesi and Nemeti were not claiming that chronology violation was acceptable. They were identifying a conditional. If you want to avoid both the infinite acceleration and the divergent blue shift, then you need closed time-like curves. If you refuse closed time-like curves, then one or both of those obstacles remain. The escape route they found led through forbidden territory. The path around the blue shift problem required violating causality. This is not a solution. This is a trade-off. Hypercomputation in exchange for time travel. Solving the halting problem in exchange for abandoning the structure of cause and effect. The price is too high, the territory is too dangerous, and so the signal degradation problem remains. There have been other attempts. Other researchers have proposed other encoding schemes, other error correction protocols, other ways to protect the signal from the blue shift, but none has definitively overcome the fundamental obstacle. The noise grows without bound, the energy density diverges, the information, if it was ever there, is lost in the catastrophe. Think of it this way. Imagine you are waiting for a message. The message is a single bit, yes or no, halt or run forever. The messenger is falling toward you from infinitely far away, across infinite time. They have the answer. They are sending it. But between you and them is a wall of light, a wall that grows brighter every moment, a wall that contains every photon that ever fell into this place, all of them compressed into the final instant before you cross the threshold. The message is in there somewhere, the signal is buried in the noise, but the noise is infinite and your receiver is finite and there is no filter that can separate the one from the other. The protocol is elegant, the geometry permits it, the mathematics balances, but the physics intrudes, and the physics is unforgiving. Rest with that for a moment. The Cauchy horizon, which seemed like a doorway, is guarded by light itself. The inner surface of the Kerr black hole, where determinism fails and hypercomputation beckons, is shielded by the accumulated radiation of eternity. You can approach it, you can fall toward it, but you cannot receive a clear signal through it. The blue shift sees to that, and yet the story continues. Because the Kerr black hole is not the only candidate, because the instability, though severe, is not the final word, because physicists and philosophers have found other venues, other geometries, other ways the equations might permit what the Kerr interior forbids. The door that closes here may open elsewhere. The geometry is vast. The catalogue of solutions is deep. And the question of whether Turing's border can be crossed, whether the undecidable can be decided, whether the unreachable can be reached, is not yet fully answered. The Cauchy horizon is unstable. The signal is degraded. The protocol, in its simplest form, fails. But simplicity is not the end of the argument. There are other paths, other proposals, other attempts to find a space-time where the geometry permits what the physics does not destroy. The journey is not over. The question remains open, and the equations, for all their hostility, have not yet spoken their final word. So the Kerr interior closes. The blue shift wins. The inner horizon, for all its mathematical promise, cannot deliver a clean signal. But the geometry of general relativity is not a single room. It is a vast architecture, a library of solutions, And not every page describes a black hole. Some describe the universe itself. In the years following the initial wave of Malament-Hogarth research, a small community of logicians and physicists began to ask a different question. What if the hypercomputer does not need a singularity? What if it does not require a descent into gravitational collapse, a journey past an event horizon, a fall toward infinite density? What if the mechanism could be gentler? Not the catastrophic throat of a black hole, but the slow, patient expansion of space itself. This is the second front in the story. The pivot away from Kerr, away from Reissner-Nordstrom, away from the violent interiors of collapsed stars. The pivot toward cosmology. The names most closely associated with this turn are István Nemetty and Hajnal Andrejka, Hungarian logicians who had spent decades working at the intersection of mathematical logic and the foundations of physics. Nemetty in particular had long been interested in what computation might mean in a relativistic universe. Not computation as we perform it on Earth, bounded by flat spacetime and slow velocities, but computation as the equations of general relativity might permit it, stretched across curved geometries and dilated times. Their insight was deceptively simple. The Malament-Hogarth condition does not require a black hole. It requires only a particular relationship between two world lines, one of infinite proper length, one of finite proper length, with the infinite line entirely in the causal past of a point on the finite line. The black hole interiors provided this relationship, but they came with baggage, singularities, Cauchy horizons, blue-shifted radiation, mass inflation. The question Nemetty and Andrejka asked was whether the same relationship could arise in a spacetime without those features, a spacetime that was in some sense friendlier. And they found one. Or rather, they found a class of them. The key was the discovery that changed cosmology at the end of the 20th century. The discovery that the expansion of the universe is accelerating. In 1998, two teams of astronomers, working independently, published results that would earn the 2011 Nobel Prize in Physics. The Supernova Cosmology Project, led by Saul Perlmutter, and the High-Z Supernova Search Team, led by Brian Schmidt and Adam Rees, had been measuring the brightness of distant type Ia supernovae, stellar explosions so uniform in their intrinsic luminosity that they serve as standard candles, cosmic mile markers that allow astronomers to measure the expansion history of the universe. What they found was unexpected. The supernovae were fainter than they should have been. The universe was not slowing down under its own gravity, as most cosmologists had assumed. It was speeding up. Something was pushing it apart faster and faster, and that something was given a name: dark energy. The simplest model of dark energy is the cosmological constant, the term Einstein himself had introduced into his field equations in 1917, then abandoned when the universe turned out to be expanding. In a universe dominated by dark energy, the geometry approaches what physicists call de Sitter spacetime, a solution to Einstein's equations with a positive cosmological constant, describing a universe that expands exponentially forever. De Sitter spacetime is well understood. It is isotropic, meaning it looks the same in every direction. It is homogeneous, meaning it looks the same at every point. It is, in a sense, the simplest possible expanding universe, and it has properties that Nemetty and Andrejka recognized as potentially useful. In a de Sitter universe, or in the de Sitter-like phase that our own universe is entering as dark energy comes to dominate, space expands faster than light can cross it. Distant galaxies are carried away from us not because they're moving through space, but because the space between us is stretching. And if the expansion is exponential, then there exists a horizon, not an event horizon in the black hole sense, but a cosmological horizon. Beyond a certain distance, light emitted today will never reach us no matter how long we wait. The universe, vast as it is, has an edge that recedes forever. This expansion creates a peculiar asymmetry in time. An observer who remains stationary, coasting through the de Sitter geometry, experiences infinite proper time stretching into the future. But the coordinate time in which distant events unfold is compressed. The light from increasingly distant regions is increasingly redshifted, the opposite of the blue shift problem inside black holes. And crucially, certain trajectories through this geometry can accumulate infinite proper time while remaining in the causal past of a finite event. Let that settle for a moment. The mechanism is not a singularity. It is not a Cauchy horizon. It is not a descent into gravitational collapse. It is simply the expansion of space, carrying an observer outward on a trajectory that stretches their experienced time without bound, while another observer, following a different path, reaches the rendezvous point in finite time. Nemeti and Andrejka sketch the protocol. Alice, the computer, does not fall into a black hole. She accelerates outward, riding the expansion of space, her world line stretching longer and longer as the universe carries her toward regions we will never see. Bob, the receiver, follows a different trajectory, one that brings him to a point where Alice's entire infinite journey lies in his causal past. If Alice's computation halts, she sends the signal. If Bob receives it, the answer is yes. If he does not, the answer is no. The geometry permits the communication. The expansion provides the infinite time. No singularity is required. The device, in principle, could decide the halting problem. It could settle whether arbitrary Turing machines halt or run forever. It could, in theory, determine whether ZF set theory, the standard foundation of modern mathematics, is consistent. The undecidable, accessible, the unreachable, reachable. Not through the violence of gravitational collapse, but through the patient stretching of cosmic time. There is something almost gentle about this version of the protocol. No catastrophic event horizon, no mass inflation, no blue shift wall, just expansion, motion, and the geometry of time itself. The computing substrate is not a collapsing star, it is the universe. But gentleness does not mean feasibility. The cosmological route has its own obstacles, its own implausibilities, its own reasons why physicists nod thoughtfully and then decline to build the machine. The accelerations required, while not infinite, are sustained over cosmological timescales. The energies involved are beyond any technology we can imagine. The distances are not merely astronomical but transcosmic. Alice does not simply fly to another galaxy. She rides the expansion beyond the observable universe into regions that will never again be causally connected to Bob's location. The protocol requires not just a rocket, but a rocket that can operate for billions of years, maintaining course across distances that dwarf everything humanity has ever contemplated. And yet the mathematics works. The equations balance. The geometry permits what the Kerr interior forbade. A Malament-Hogarth configuration without the Cauchy horizon catastrophe, without the divergent blue shift, without the mass inflation singularity. The signal, in this version, is not compressed by infalling radiation. It travels through expanding space, redshifted perhaps, but not infinitely amplified. The noise problem, at least in its most virulent form, does not appear. This is not a blueprint, it is a proof of concept. A demonstration that the equations of general relativity, applied to the universe we actually live in, contain at least the geometric possibility of hypercomputation. The black hole route may be blocked by instabilities, but the cosmological route remains open, mathematically open, if not practically constructible. The distinction matters. The question is not whether we can build a Malament-Hogarth computer tomorrow, or in a century, or in a million years. The question is whether the laws of physics permit such a computation in principle, whether the border Turing drew is a law of nature or merely a law of our particular circumstances, whether undecidability is absolute or merely local, true for beings trapped in flat spacetime and finite time, but not for beings who could ride the expansion of the cosmos itself. And this is where the scientific community stands, not in acceptance, but not in dismissal either, in a careful suspension, a posture of principled agnosticism that takes the mathematics seriously while declining to claim that the protocol is constructible. The philosophers of physics have been particularly attentive to this question. John Norton, whom we met earlier in this story as co-author with John Earman of the foundational 1993 paper, has continued to think carefully about what Malament-Hogarth spacetimes mean for the relationship between physics and computation. The obstacles he and Earman identified, the reliability problem, the signal degradation problem, the failure of global hyperbolicity, remain serious. But they are not, in Norton's view, sufficient to dismiss the idea as physically irrelevant. The spacetimes are valid solutions to Einstein's equations. The protocols are mathematically coherent. The question of whether any such spacetime is physically realizable is genuinely open. Christian Wüthrich, a philosopher of physics at the University of Geneva, has explored the implications of Malament-Hogarth spacetimes for our understanding of determinism and the structure of physical theories. His work touches on the deep question of what it means for a spacetime to be physically reasonable. The standard criterion, global hyperbolicity, the property that guarantees determinism and well-posed initial value problems, is violated by all Malament-Hogarth spacetimes. This is not an accident. It is a consequence of their defining feature, the presence of world lines with infinite proper length in the causal past of finite events. Global hyperbolicity and Malament-Hogarth geometry are incompatible. You cannot have both. This is why Penrose's cosmic censorship hypothesis looms over the entire discussion. Cosmic censorship, in its strong form, asserts that all physically reasonable spacetimes are globally hyperbolic, that nature forbids the naked singularities and Cauchy horizons that would otherwise permit hypercomputation. If cosmic censorship is true, then Malament-Hogarth spacetimes are not physically realizable, however mathematically valid they may be. The equations permit them, nature forbids them. But the status of cosmic censorship is far from settled. Penrose proposed it as a hypothesis, not a theorem. Decades of research have produced partial results, counterexamples and ongoing debate. There are spacetimes that violate cosmic censorship and appear to be physically reasonable. There are stability arguments that support it and stability arguments that complicate it. The conjecture is one of the great open problems in general relativity, and its resolution, if it ever comes, will have direct implications for whether hypercomputation is physically possible. Juliusz Dobroszewski, a philosopher of physics who completed his doctoral work at Jagiellonian University in Krakow, has focused specifically on spacetime singularities and global structure. His research addresses exactly the questions that Malament-Hogarth spacetimes raise. What does it mean for a spacetime to have pathological features? When do those features disqualify a solution as unphysical? The answers are not obvious. General relativity is a permissive theory. It admits solutions with closed time-like curves, solutions with naked singularities, solutions with regions where the future cannot be predicted from the past. The question of which solutions describe possible universes and which are mere mathematical curiosities is a question about physics, not mathematics, and physics has not yet delivered a definitive answer. The consensus, such as it is, might be summarized this way. Malament-Hogarth spacetimes are taken seriously, but not accepted. They are legitimate objects of study, not crackpot speculation. The protocols they permit are coherent, not confused. But no one claims that we can build the machine. No one claims that the obstacles, the accelerations, the energies, the timescales, the instabilities, can be overcome with any technology we can envision. The spacetimes are stress tests of physical law, probes of the relationship between geometry and computation, not blueprints for engineering. This is a peculiar epistemic status. The idea hovers in a space between physics and philosophy, between mathematics and metaphysics. It is not falsified, because the spacetimes are valid solutions. It is not confirmed, because no one has built the computer. It is not even clearly falsifiable, because the obstacles are practical rather than principled. Matters of energy and time and distance, not matters of logical contradiction. And perhaps that is the point. Perhaps the value of Malament-Hogarth spacetimes lies not in what they allow us to build, but in what they force us to think about. The relationship between physics and computation, the status of mathematical truth, the meaning of undecidability in a universe governed by general relativity. Which brings us to the question we have been circling since the beginning, the question that Turing's work made precise but did not answer, the question that Gödel's theorems illuminated but did not resolve. What would it mean to know the unknowable? In 1931, 5 years before Turing submitted his paper on the Entscheidungsproblem, Kurt Gödel published a result that shattered the foundations of mathematics. His first incompleteness theorem, presented in a paper titled On Formally Undecidable Propositions of Principia Mathematica and Related Systems, established that any consistent formal system capable of expressing basic arithmetic contains true statements that cannot be proven within the system, not merely unproven, unprovable, statements whose truth is real but whose demonstration is forever beyond the reach of the axioms. This was not a failure of cleverness. It was not a limitation that better mathematicians might overcome. It was a structural feature of formal systems themselves, a boundary built into the architecture of logic. Gödel showed that there can be no mathematical theory of everything, no single set of axioms from which all mathematical truths can be derived. The provable and the true are not the same. They overlap, but they do not coincide, and the gap between them is permanent. The halting problem, which Turing would formalize 5 years later, is a computational cousin of Gödel's result. It asks whether there exists an algorithm that can determine, for any arbitrary program and input, whether the program will eventually halt or run forever. Turing proved that no such algorithm exists. The question is undecidable, not merely unsolved, but unsolvable by any finite procedure. These results define the borders of formal knowledge. They tell us that mathematics, for all its precision and rigour, contains truths it cannot prove and questions it cannot answer. The Gödel sentences, statements that assert their own unprovability, are true if the system is consistent, but their truth cannot be demonstrated within the system. The halting problem, the question of whether a given computation terminates, has an answer for every specific case, but no general method can find that answer for all cases. Now imagine a physical hypercomputer, a device that exploits Malament-Hogarth geometry to complete an infinite computation in what appears, from the right vantage point, to be finite time. Such a device could, in principle, solve the halting problem. It could run any program for an infinite number of steps and send a signal if and only if the program halts. It could answer questions that no Turing machine can answer. But what would such an answer mean? Here is the tension, and it cuts to the heart of what mathematics is. If you believe, with the mathematical Platonist, that mathematical truths exist independently of any formal system, that the integers are real, that the truths about them are facts about an abstract realm, then a physical measurement of an undecidable statement's truth value would be a genuine discovery. The hypercomputer would be a telescope pointed at mathematical reality, revealing truth that no proof could reach. The answer it delivers would be true in the fullest sense, even though it was not derived from axioms. But if you believe, with the formalists, that mathematical truth is constituted by derivability, that a statement is true if and only if it can be proven from the axioms, then the hypercomputer's output would be something else entirely. It would be an empirical measurement, a physical fact about a physical system, but not a mathematical proof. The device might tell you that ZF's set theory is consistent, but this would not constitute a proof of consistency within ZF. It would be data, not demonstration, an observation, not a theorem. The distinction is not merely academic. It touches on what we mean by knowing, what we mean by truth, what we mean by the relationship between the physical universe and the abstract realm of mathematics. Consider what the hypercomputer would actually do. It would run a Turing machine for an infinite number of steps. If the machine halts, it sends a signal. If the signal arrives, the observer knows the machine halts. If the signal does not arrive, the observer knows the machine runs forever. This is a physical process producing a physical result. The signal is made of photons or particles or gravitational waves. The observation is made by a physical brain or a physical detector. The knowledge gained is knowledge about the behavior of a physical system. But the halting problem is a question about abstract computation. The Turing machine being simulated is not a physical device. It is a mathematical object defined by rules and states and transitions. The question of whether it halts is a question about an infinite sequence of abstract operations. How can a physical measurement answer an abstract question? One response is to say that the hypercomputer is not answering the abstract question directly. It is simulating the abstract computation with perfect fidelity and reporting the result. If the simulation is faithful, the answer is the same. The physical and the abstract align because the physical system is implementing the abstract procedure. But this raises further questions. How do we know the simulation is faithful? Over infinite time, even the most reliable physical system might err. The reliability problem that Ehrman and Norton identified, the impossibility of guaranteeing error-free operation over infinite duration, looms here too. And if the simulation is not perfectly faithful, then its output might not reflect the truth about the abstract computation. Another response is to bite the bullet and accept that physical hypercomputation would change what we mean by mathematical knowledge. If a physical process can determine the truth value of an undecidable statement, then perhaps the provable true distinction needs to be revised. Perhaps mathematical truth is, in some sense, empirical after all, accessible not through pure reasoning but through observation of the right physical systems. This is a radical position, and few mathematicians or philosophers hold it comfortably. But the existence of Malament-Hogarth spacetimes forces the question: if such spacetimes are physically realizable, even in principle, then the relationship between provability and truth is not merely a logical curiosity. It has physical implications. The universe might contain systems that can access truths no formal proof can reach. Let that settle for a moment. We are not claiming that such systems exist. We are not claiming that they can be built. We are claiming only that the equations of general relativity, our best theory of space and time and gravity, do not rule them out. The mathematics permits them. The physics, well, the physics is not yet fully understood. The cosmic censorship hypothesis might forbid them. The instabilities might destroy them. The energies might be forever beyond reach. But the door is not closed. The equations leave it ajar. And this is the intellectual climax of the story. Not a resolution, but an opening. The discovery that Turing's border, the wall between the decidable and the undecidable, might be a feature of our particular circumstances rather than a law of nature. The possibility, not the certainty, but the genuine possibility, that the unreachable might be reached, if only we knew where to look and how to listen. The philosophers debate, the physicists calculate, the spacetimes remain valid, the protocols remain coherent, the obstacles remain formidable, and the question, whether a physical process can settle what logic cannot, remains open. Think about what that means. For 80 years since Gödel's theorem and Turing's proof, we have lived with borders, limits to what can be proven, limits to what can be computed, limits that seemed as fundamental as the speed of light, as inviolable as the second law of thermodynamics. And now we find that those limits might be contingent, dependent on the geometry of space-time, different in different universes, different along different world lines, different for observers who can access different causal structures. The undecidable might not be absolutely undecidable. It might be undecidable for us, here, now, in this flat patch of space-time with our finite lives and our finite machines. But somewhere else, someone else, along a world line we cannot follow, the answer might be knowable. The halting problem might be solvable. The Gödel sentences might be decidable. The border might be crossable. This is not mysticism. It is not wishful thinking. It is a consequence of taking general relativity seriously, of following the equations where they lead, of asking what computation means in a universe where time is not absolute and geometry is not fixed. The result is strange. The result is unsettling. The result leaves us with more questions than we started with. But the questions are the point. The questions are what drive the inquiry forward. And the inquiry is not finished. Rest with that for a moment. Let the scale of it settle. We began with Turing in a study in Cambridge, asking what a machine could compute. We travelled through Einstein's equations, through Schwarzschild and Kerr, through the interiors of black holes and the instabilities of Cauchy horizons. We found that the geometry permits what intuition forbids. Infinite computation completed in finite time, signals sent across infinity, answers to questions no algorithm can answer. We found that the physics is hostile, that the obstacles are severe, that no one claims the machine is buildable. But we also found that the door is not closed, the cosmological route remains open, the equations still permit, and the question of what it would mean to know the unknowable, to hold in your hands the answer to an undecidable question, that question now belongs not just to logic but to physics. The mathematicians and the physicists have drawn their borders, but the borders are not where we thought they were. The map is stranger than the territory we imagined, and yet there is a final wrinkle, a last complication that the philosophers have circled for decades, and it cuts deeper than any instability, any blue shift, any engineering impossibility we have yet considered. It concerns not the computation itself, but what happens after. Not whether the answer can be generated, but whether the answer can mean anything once it arrives. Suppose for a moment that every obstacle falls away. Suppose the cosmic censorship hypothesis is wrong, or incomplete, or admits exceptions we have not yet discovered. Suppose the Cauchy horizon instabilities can be navigated. the signals preserved, the energy requirements met by some future civilization whose capabilities dwarf our own. Suppose Alice completes her infinite computation, runs the universal Turing machine through every possible configuration, checks every candidate program, sends her signal at the precise moment the machine halts. Suppose Bob receives that signal, arriving at the Malament-Hogarth event with the answer encoded in a single photon, a single bit, a yes or a no to a question that no finite procedure could ever have answered. What then? Bob has the answer. Bob knows whether the program halts, but Bob is one observer at one event in one location in spacetime, and the answer he holds cannot be verified by any finite procedure. That is the definition of what he has received. If it could be verified by running a finite computation, it would not be an answer to an undecidable question. The very property that makes the result meaningful, that it transcends what any algorithm can compute, is the same property that makes it uncheckable, unreproducible, inaccessible to the methods by which we ordinarily establish truth. This is not a technical problem. It is not a matter of improving our instruments or extending our lifetimes. It is built into the structure of what undecidability means. John Earman and John Norton, in their 1993 paper, were careful to note this limitation. They wrote that even if the protocol succeeds, the result is epistemically fragile. It is a fact that exists at a single point, for a single observer, and cannot be communicated to the rest of the universe in a form that permits independent confirmation. Picture it this way. Bob arrives at the rendezvous point. He checks his receiver. The signal is there, or it is not. He now knows something that no finite mind could have computed. But when he tries to share that knowledge, he faces an insurmountable barrier. He cannot demonstrate the truth of his claim. He cannot run the computation himself to verify it. The whole point is that the computation is unrunnable in finite time. He cannot point to a proof, because the result is not the kind of thing that admits proof in any formal system. He can only say, I was there, I received the signal, the answer is yes. And everyone else in the universe must take his word for it. There is an analogy here, one that physicists have struggled with for nearly a century. In quantum mechanics, there exists what is called the measurement problem. Before observation, a quantum system exists in a superposition of states, the famous cat that is both alive and dead. The act of measurement collapses the superposition into a definite outcome. But here is the difficulty. The outcome is irreducibly tied to the observer who performs the measurement. It cannot be rewound. It cannot be checked by another observer going back and repeating the exact same measurement on the exact same system, because the measurement itself has changed the system. The result is real, but it is also singular, unreproducible, bound to a specific moment and a specific perspective. The Malament-Hogarth computation suffers from a similar fate. The answer Bob receives is not embedded in any structure that persists, that can be examined, that can be subjected to the usual methods of scientific verification. It is a one-time event, a flash that illuminates and then vanishes. The universe has computed something, but the universe cannot check its own work. Let me try once more to give you a feel for that. Imagine you are Bob. You have travelled to the edge of a black hole, or you have surfed the accelerating expansion of the cosmos, or you have found some other Malament-Hogarth geometry that the physicists have not yet ruled out. You have waited your finite time while Alice, somewhere far away, has lived through eternity, and now, at this moment, you know the answer to a question that has haunted mathematics for a century. You know whether a specific Turing machine halts. You know something that Gödel proved could not be proven, that Turing proved could not be computed, that the entire edifice of 20th century logic declared forever beyond reach. And you cannot tell anyone, not because they would not believe you, not because the technology to transmit the information does not exist, but because the very nature of what you know resists transmission. The moment you try to share it, you're asking others to accept a result without any means of verification. You're asking them to trust a process they cannot observe, a computation they cannot repeat, a signal they cannot examine. You have become the sole witness to a truth that admits no other witnesses. This is the deepest irony of the Malament-Hogarth spacetime. It offers a loophole in the laws of computation, but the loophole closes behind you as you pass through it. The answer is real, but it is also private. The universe has done something that should be impossible, and no one will ever be able to prove it. Some philosophers have argued that this renders the entire enterprise meaningless. If a result cannot be verified, they say it is not knowledge. It is just an event, a configuration of particles at a particular location, no different from a random fluctuation, a cosmic ray striking a detector, noise in the void. What distinguishes knowledge from noise is precisely the capacity for confirmation, for reproducibility, for independent access. Strip that away, and you have not gained knowledge at all. You have only gained a private experience that happens to correlate with a mathematical truth. Others disagree. They point out that the correlation is not accidental. The spacetime geometry guarantees it. The causal structure ensures that if the signal arrives, the computation was completed. If it does not, the computation runs forever. The answer is not a guess. It is not a belief. It is a physical fact, inscribed in the causal history of the universe, as real as any other physical fact. That it cannot be checked does not make it less real. It only makes it less useful. And perhaps that is the most honest summary of where we stand. The Malament-Hogarth spacetime, if it exists, would produce answers that are real but unreachable, truths that are true but unprovable, knowledge that is knowledge but cannot be shared. The cosmic computer runs its infinite errand, and the result arrives at a single point, for a single observer, and then disperses into the ongoing flow of time like a whisper in an empty cathedral. The universe might know the answer to the halting problem, but it might never be able to tell us. Rest with that for a moment. We have travelled a long road. We began in autumn in Princeton, with a young mathematician named Alan Turing and a question about the limits of computation. We followed the thread through Gödel's incompleteness, through the halting problem, through the discovery that mathematics contains borders that cannot be crossed by any finite procedure. We watched as those borders seemed to harden into laws, as solid and as final as the speed of light. And then we stepped into Einstein's universe. We found that general relativity, our best theory of space and time, does not respect the borders that logic drew. The field equations contain solutions, valid, consistent, mathematically rigorous solutions, in which infinite computation can complete in finite time. Malament noticed the geometry, Hogarth formalised the protocol, Ehrman and Norton catalogued the obstacles, and the question shifted from whether such spacetimes are logically possible to whether they are physically real. The answer remains, we do not know. The Kerr interior offers a venue, but the blue shift destroys the signal. The cosmological expansion offers a friendlier geometry, but the distances and energies are beyond any conceivable technology. Every candidate faces its own catastrophe, its own barrier, its own reason for skepticism. And yet none of the obstacles is a proof of impossibility. The cosmic censorship hypothesis remains a hypothesis. The instabilities might admit exceptions. The engineering might be achievable by minds vastly different from our own. The equations leave the door ajar. Let me return now to where we began. Not to the content, we will not repeat what has already been covered, but to the image that opened this journey and that now returns with new weight. Einstein's field equations. 10 interlocking expressions relating the curvature of spacetime to the distribution of energy and matter. Written in tensor notation, they fit on a single line. Written out in full, they fill pages with indices and derivatives and covariant components. But their meaning is simple. They tell us how the universe bends, how mass and energy warp the geometry that everything else must follow. And they tell us, if we listen carefully, what kinds of universes are permitted. Among the permitted universes are the strange ones, the ones with closed, time-like curves and naked singularities and Cauchy horizons that flicker with instability, the ones where time loops back on itself, where the past is not fixed, where infinity fits inside a finite interval. These are not errors. They are not bugs in the equations. They are features, logical consequences of the mathematics that describes gravity and light and the shape of existence. And among those features is the Malament-Hogarth spacetime. Picture it one last time, 2 world lines. One is Alice's, stretching out through infinite proper time, carrying her computation through an endless sequence of steps. The other is Bob's, finite, bounded, arriving at a single point where the infinite journey is already complete. The 2 lines do not run parallel. They curve toward each other, shaped by the geometry of the spacetime they inhabit. And at the Malament-Hogarth event they meet. The future of Bob touches the completed past of Alice. The finite receives the infinite, and the answer arrives. That is the image. Two paths through space-time, one without end, one with a destination, meeting at a point where the impossible becomes possible, not a solution, but a question. The most precise question physics has ever allowed us to ask. Can the geometry of the universe exceed the limits of computation? We cannot answer yes. The obstacles are too severe, the instability is too pervasive, the consensus of physicists too cautious. We cannot point to a Malament-Hogarth spacetime and say, there it is waiting to be used. The cosmos is not a laboratory we can control. But we also cannot answer no. The mathematics permits. The equations do not forbid. Every attempt to rule out these spacetimes has run into uncertainty, the cosmic censorship hypothesis unproven, the stability analyses incomplete, the energy conditions violated but not impossibly so. The door that should be closed remains cracked open. And so we are left with the question itself. Not the answer, the question. That is what we carry away from this journey. Not a resolution, but an opening. The discovery that the border between the decidable and the undecidable might not be absolute. That it might depend on where you stand, what path you take through the curved landscape of space-time, what geometries you can access and inhabit. The undecidable might be undecidable for us. For finite creatures, in a flat patch of space-time with our bounded lives and our bounded machines. But the universe is larger than us. The equations contain more than we can reach. And somewhere, in some configuration of mass and energy and curvature, the answer might be knowable. The border might be crossable. The wall might be, in some deep sense, local. Think about what that means for mathematics. For a century, we have believed that the incompleteness theorems and the halting problem reveal something fundamental about the structure of truth itself. Limits that cannot be exceeded, borders that cannot be crossed, questions that must forever remain unanswered. And now we find that those limits might be features of our computational architecture, not laws of logic. That a different architecture, one embedded in a different space-time, might exceed them. The absolute becomes contingent. The necessary becomes local. The wall becomes a horizon, and horizons can be approached even if they can never be touched. And think about what that means for physics, for the relationship between the mathematical universe and the physical one. We have always assumed that mathematics describes physics, that the equations are models, approximations, maps of a territory we can never fully access. But the Malament-Hogarth spacetimes suggest something stranger. They suggest that physics might exceed mathematics, that the physical processes permitted by general relativity might accomplish what no formal system can prove, what no algorithm can compute, what no finite mind can conceive. The territory might be larger than any map. Let that settle for a moment. Let the weight of it press gently. We began with limits, with the discovery in the early 20th century that mathematics contains questions it cannot answer and computations it cannot complete. Those discoveries felt like endings, walls where roads should be. The universe seemed smaller after Gödel and Turing, its possibilities bounded by theorems that admitted no exceptions. But the universe, we have learned, is not simple. The equations are not simple. The geometry of space-time contains chambers we have not yet entered, corridors we have not yet mapped, configurations that defy the intuitions we built in flat, safe, finite regions. And in those configurations, the limits we thought were final might turn out to be provisional. The endings might become openings. The walls might become thresholds. Nobody knows whether Malament-Hogarth spacetimes exist in nature. Nobody knows whether the obstacles can be overcome, whether the instabilities can be navigated, whether the signals can be preserved across the chasms of curved spacetime. The physicists remain skeptical. The philosophers remain cautious. The consensus is that these are mathematical curiosities, not physical possibilities. But the equations do not say that. The equations say, this is permitted, this is consistent, this does not violate the rules we know. And so the question remains open. The deepest question we have asked in this journey, whether a physical process can settle what logic cannot, whether the universe computes more than we can compute, whether the undecidable is really undecidable or just undecidable for us, that question has no answer. Not yet. Perhaps not ever. But the question exists. The question is real, and the question is new. Before Malament and Hogarth, before Ehrman and Norton, before the careful analysis of Kerr interiors and cosmological expansions and Cauchy horizon instabilities, we did not know to ask. The limits seemed absolute, the borders seemed final. The undecidable was simply undecidable, a feature of logic itself, beyond the reach of any physical process. Now we know that the question is open. Now we know that the equations permit. Now we know that the architecture of spacetime might, in principle, exceed the architecture of computation. That knowledge is not a solution. It is not a tool. It is not a technology waiting to be built. It is something more fragile and more valuable. It is the discovery that we do not know where the boundaries are, that the universe might contain more than we imagined, that the questions we thought were closed might still be questions, and so we end where we began, with uncertainty, with openness, with the recognition that the inquiry is not finished, that the map is incomplete, that the territory stretches beyond every border we have drawn. Two world lines, one infinite, one finite, their futures touching at a single point, where the endless meets the bounded, where the computation completes, where the answer arrives. The geometry permits it, the physics doubts it, the question remains, and somewhere in the curved and silent reaches of spacetime the equations wait, patient as they have always been, containing their secrets, holding their doors ajar. The universe might know things we cannot know. It might compute what we cannot compute. It might hold answers to questions no mind has ever asked, no algorithm has ever run, no formal system has ever proven. Or it might not. We cannot say. We may never be able to say. But the question, that precise, beautiful, vertiginous question, belongs to us now. It belongs to mathematics and physics both. It belongs to the border between them, where the computable meets the geometric, where Turing's limits brush against Einstein's curves. You can let that thought hold you if you like. The night is quiet, the equations are still, and the question, the oldest question dressed in its newest form, drifts gently through the dark. Is the impossible merely improbable? Is the unreachable merely unreach? Is the border a wall, or is it only a horizon, vast, patient, waiting for us to find the path? The universe does not answer, but it leaves the door ajar,